In this problem, we're going to perform finite element analysis on a bar that is axially loaded with a force of 1,346 newtons. And we're going to figure out not the axial strain in the direction of the loading, but the axial strain in the direction of the height of the bar. To do this, let's go ahead and first do some hand calculations and draw out the diagram that we use similar to that of question 1. And we have a bar with some cross-sectional area A, and we have a load being applied to the end in the axial direction. We're interested in the strain at some location along the bar, and we're more or less assuming that this strain is going to be the same along the bar. And instead of the axial strain, which we looked at last time, so let's say the sigma leading to the epsilon x, what we're interested in is looking at what the strain in, say, a y direction might be, or orthogonal to it, so in the vertical direction. And for this, we can use a relationship that we've brought out previously that relates the strain in a given direction to the stress in that direction, as well as the Poisson ratio's effect on orthogonal stresses in the problem that we might be studying. So, with this equation, we recognize that sigma y is 0. We also recognize that sigma z is 0, while sigma x is non-zero. So we can go ahead and write, well, sigma y equals sigma z equals 0, and then we simplify this expression for epsilon y, and we see that we're really going to be concerned about the Poisson ratio's effect on sigma x, and it's going to help us give a value for epsilon y. And if the parameters were similar to what we used last time, they are a little bit different. The height and the width of the beam are different. But if they were the same, what you would see is a Poisson's ratio essentially knocking down the strain from what we calculated in the last problem, okay? Because Poisson's ratio is going to be less than 0.5. We can plug in some numbers here, and let's go ahead and put them in Google to figure out what the resulting values might be. So we'll have a negative 0.2 times 1346 newtons, and we're going to divide by 118 gigapascals times this 2 centimeters squared, like that. Let's see what we get. Okay, so we're going to have in microstrain, because we can multiply by 1e6 minus 5.7 microstrain. Okay, and if we think about it, the way we've drawn epsilon y is coming out orthogonal to the direction that the axial force is being applied, and it's going to be negative because it's going to be shrinking in that direction. So let's go ahead and begin our finite element analysis of this problem by first looking at what we have in the geometry. So for the geometry, we're going to use FreeCAD again. And we see that it's going to be a bar with a length of 15 centimeters, and it has a width of 2 centimeters and a height of 2 centimeters. So we can go ahead and create a new part. We go down to the workbench for part, we hit cube, and we can click on cube, and then change the length to 150 millimeters, that'll be 15 centimeters, and we have to change the width to 20 millimeters, or 2 centimeters, and the height to 20 millimeters as well. So now, if we have this system, or this bar like this, okay, what do we see? We see that, oops, let's see, oh, there we go, all right. It looks like a bar. And we'll go ahead and we'll export this bar. We'll call this, okay, session 8, Q2, as an STL file. And if I'm going too fast here, you can go back and look at the previous examples that we've Okay, yeah, let's do this that we've described. So we're going to go to the downloads folder, and here we have PrePoMax. The development version will run the PrePoMax executable file, and we'll go ahead and create a new. I'm going to go a little faster than I did last time, and we're going to go ahead and import the geometry. That's this session 2 STL. We see that it's too large. It's a factor of 1,000 too large, like we described last time. So we'll transform, scale, and we'll do 1/1000th in the 3 directions, like we have here. And we'll go ahead and close that. The part has disappeared, so we do zoom to fit. And if we look at this, good. That's looking kind of like what we had last time. We'll go ahead and create our mesh parameters, and we're going to do that on the part, and then we're going to say, okay, so this is 2 centimeters by 2 centimeters cross section, and it's 15 centimeters long, so it's a little bit different. Let's go ahead and we'll say that that we're going to make it so the minimum size is maybe 5. Let's see what that looks like. Okay, and then we'll come over here and mesh, create the mesh. Yeah, that's probably not too bad. It's not the greatest, but it's not too bad. So we'll leave that like that. Once again, we are going to create a reference point, and this one's 15 centimeters down, so we'll do 0.15, and then we need actually 0.01, 0.01. Okay, puts it right there. Then we'll also create a surface. I guess I jumped that. And a surface we're going to put on this face right there. We hit OK. The material we're going to create. I don't remember what the elastic modulus was. If we come over here, we see that it is 118 gigapascals, and the Poisson ratio is 0.2. So let's go back. Elastic modulus will be 118, and the Poisson's ratio will be 0.2. Hit OK. We are going to create a section that corresponds to the part, the whole beam. Hit OK. And for constraints, we can create a rigid body. We're going to select this surface. Oh, actually, we're going to select the surface here. Good. Hit OK. So now we've got that. We're going to come over here. We're going to create a static step. Hit OK. And then we're going to create a boundary condition fixed on this side. Right here. Okay. So hit OK. And then we're going to create a load, the concentrated force. This is going to go on our reference point that we had created over here. And this one is 1346. So 1346 newtons. That. Okay, it's coming out of face. We can run the analysis. Yes, go ahead and overwrite whatever you had. Okay, and this one is pretty fast. In a couple of seconds, we look at the results. And we kind of went through these different things last time. We'll jump over to the strain. And epsilon 1,1, okay, would be in the axial direction, so in the x direction. And what we're interested in is in the height, so epsilon 2,2. Right? And if we come over and right click and then do a query, let's say right there, what do we get? We get a value of minus 5.7 times 10 to the minus 6 strain. What do we calculate in our previous hand calcs? We got minus 5.7. That's excellent. Minus 5.703. Okay, so it's an extreme agreement, and if we were to solve this problem or upload it to Canvas, as is required for the class, make sure you take an appropriate screenshot that shows your value of strain, and then make sure you also insert the appropriate value of strain here. And highly suggest again that you make sure you do the whole problem first, calculating things out, make sure you get agreement, and then go ahead and upload your results. Well, I hope this problem was somewhat helpful, and that we got a little bit more experience to understand how to do finite element analysis and determine an orthogonal strain to the direction of loading with a bar. Thank you.